And welcome back to our next lesson in astronomy. We are now going to do a little bit of a time walk and look at ancient astronomy and how that helped set the foundation for a modern understanding of how astronomy works. So the best way to start this off is to look at some early cosmology. Our concept of the cosmos, its basic structure and origin, is called cosmology. It's a word that actually has Greek roots. And the reason why it has Greek roots is because of the importance in ancient Greece in helping lay out some of that early foundation. Now, before the invention of telescopes, humans really had to depend on the simple evidence of their senses for a picture of the universe. The ancients developed cosmologies that combined their direct view of the heavens with a rich variety of philosophical and religious symbolism. At least 2,000 years before Columbus, sailed, educated people in the eastern Mediterranean region already knew that the Earth was round. Belief in a spherical Earth may have stemmed from the time of Pythagoras, a philosopher and mathematician who lived 2,500 years ago. He believed that circles and spheres were these perfect forms, and suggested, therefore, that the Earth should be a sphere. So let's go ahead and start off with one of the first pieces here, which is using Aristotle and his observations with the moon. Now, the writings of Aristotle summarize many of the ideas of his day. They describe, for example, the progression of the moon's phases, its apparent changing of shape, and how they result from seeing those different portions of the moon's southern hemisphere as the month goes by. Now, Aristotle also knew that from his observations, the sun must be further away from the Earth than the moon is, because occasionally the moon passed exactly between the Earth and the sun and hid the sun temporarily from view. And of course, we know this today to be a solar eclipse, but Aristotle uses to cite convincing arguments, the Earth must be round. First is the fact that as the moon enters or emerges from the Earth's shadow during an eclipse, the shape of the shadow seen on the moon is always round. Only a spherical object could produce a round shadow. If the Earth were, say, a disk, then there would be occasions when sunlight would strike its edge, and on the shadow of the moon, it would appear, therefore, as a line instead of as a round shape. So, this argument for a round world was a very important thing in helping to establish what we know about astronomy today. So Aristotle said, I have another argument. He said, what about travelers who are going south a significant distance? What do they notice? Well, they can observe stars that are not visible further north. And the height of the North Star, which of course, as you recall, is the star that is nearest to the North Celestial Pole, decreases as a traveler moves south. If the Earth were flat, everyone would see the same stars overhead. The only possible explanation that Aristotle argued is that the traveler must have moved along a curved surface, showing stars from a different angle. And we know this, of course, how the Earth is in orbit, and we obviously know this is going to affect what we perceive about the Earth's orbit. So, another Greek thinker, Aristarchus, suggested that the Earth was actually moving around the sun. So he was one of these first ones to kind of reject the geocentric model and propose more of a heliocentric idea. But Aristotle and many of the ancient Greek scholars looked at that and said, no, that can't be so. And one of the reasons they said that this model can be is that, if the Earth was moving around the sun, then they would be observing stars from different places along Earth's orbit. Now, as Earth moved along, therefore, nearby stars should shift where their positions are in the sky relative to more distant stars. And they got to them thinking about this idea of parallax. An apparent shift in the direction of object because of the motion of the observer is what we refer to as parallax. And we would call the shift in the apparent direction of a star due to Earth's orbital motion stellar parallax. Now, the Greeks did make dedicated efforts to observe stellar parallax, even enlisting the aid of some Greek soldiers with the clearest vision they had, but to no avail. The brighter and presumably nearer stars just did not seem to shift as the Greeks observed them in the spring and then again in the fall when the Earth is on the opposite side. This meant that either the Earth was either not moving or that the stars had to be so tremendously far away that the parallax shift was tremendously small. Now, a cosmos of such an enormous proportion of this extent required them to have such a leap of imagination that most of the ancient philosophers were not prepared to make this accepted view, so instead they retreated to the safety of the Earth-centric or the geocentric view, which would actually dominate Western thinking for nearly 2 millennia. But, of course, the orbit is only one piece of the planet. What about the actual measurement of the Earth? Like, how big is this body that we're sitting on in space? Well, the Greeks not only knew that the Earth was round, but they were actually able to measure its size. The first fairly accurate determination of Earth's diameter was made in about 200 BCE by Eratosthenes, who was a Greek who was actually at the time living in Alexandria, Egypt. Now, his method actually came down to some geometry, and he based this on observations of the sun. Now, as we know, the sun is pretty distant from us, and because it's so distant, all the light rays that are coming out, because it's such a great distance, are actually going to approach us and strike where we're at in a essentially parallel line. So to really kind of illustrate this, we can take a look here at this image to kind of get the idea of these parallel lines and how they could travel parallel. So let's take a source of light near Earth. Let's say at position A here in our image, we can say this ray is going to strike different parts of the Earth along a diverging path. But if we say, okay, let's place the light source at B or at C, which of course is even further away, the angle between the rays that strike opposite parts of the Earth is now a lot smaller. And because the sun itself is even further away, those rays are effectively at parallel lines. So, how did he come up with this calculation? Well, we already know he's in Egypt, and he's like, well, you know what? I've been told that the first day of summer in Egypt, sunlight is going to strike the bottom of this vertical well at noon. And so, because it hit that at noon, this indicated to him that the sun was directly over the well, meaning that it was on a direct line from the center of the Earth to the sun. At the corresponding date and time in Alexandria, he observed the shadow of columnate and saw that the sun was actually not directly overhead, but instead was slightly south of the zenith. So because the sun's rays were striking the two cities were parallel to another, why would the two rays not make the same angle with the Earth's surface? Well, he reasoned, well, the Earth has to have some curvature, and because that has curvature, it means that straight up, the zenith is not the same in the two cities. And so he was then saying, well, you know, if this is not the same thing, maybe I can measure this. And the measurement of the angle in Alexandria, he realized, allowed him to figure out the size of the Earth. So how did he actually do this between the two locations? Well, he measured the size of the Earth by observing the angle at which the sun's rays hit our planet's surface. Now, the sun's rays, like I said, come in parallel, but because Earth has a curved surface, a ray at St. comes straight down, whereas a ray at Alexandria makes an angle of about 7 degrees with the vertical. This means, in fact, that Alexandria, or surface, has curved away from St. by about 7 degrees of that 360 we would expect, or about 1/50th of a full circle. Therefore, the distance between the two cities has to be about 1/50th the circumference of the Earth. And now, of course, you know, there is some debate about how accurate this is based upon the measurements that were used. But again, it is a good way for know that some of these early calculations were done, and they were done in an approach that actually mathematically makes sense. Next ancient astronomer is going to be Hipparchus, who is perhaps considered the greatest astronomer of antiquity, and who was born in what is today present-day Turkey. He actually erected an observatory on the island Rhodes in about 150 BCE, and there he measured as accurately as possible for the time the positions of objects in the sky, compiling a pioneering star catalog with about 850 entries. Now, he designated celestial coordinates for each star, specifying its position in the sky, just as we specify the position of a point on the Earth by giving its latitude and longitude. He also divided the stars into a pair of magnitudes according to their brightness. So, for example, he said that the brightest stars were stars of the first magnitude, which would be the brightest group. And so the next group, he said, hey, you know, you're the stars of the second magnitude, and so on and so forth. And that gets us to the celestial pole. because by observing the stars and comparing his data with older observations, Hipparchus actually made one of his most remarkable discoveries. The position in the sky of the North Celestial Pole had altered over the previous century and a half. He deduced correctly that this had happened not only during the period covered by his observation, but in fact was happening all the time. The direction around which the sky appears to rotate changes slowly but continuously. If you recall, we talked about how the North Celestial Pole is just a projection of Earth's North Pole up into the sky. And if the North Celestial Pole is wobbling around, then the Earth itself must be the thing doing the wobbling. Now today we understand that the direction of Earth's axis point does indeed change slowly but regularly. We call this motion precession. And to really kind of give a good illustration of this, you can take a look at this kind of visual that we have here. Because our planet is, first off, not an exact sphere, but it actually bulges a bit at the equator from the poles of the sun and moon, and that pole causes it to wobble a little bit like a top. It takes about 26,000 years for the Earth's axis to complete one circle of precession. As a result of this motion, the point where our axis points in the sky actually changes as time goes on. To give you context, the North Celestial Pole is currently near the star Polaris, but if we were to spin the clock back about 5,000 years ago, you'd actually find it is close to a star called Thuban, and in 14,000 years, it'll be closest to the star Vega. So now we're going to move on to Ptolemy's model of the solar system. The last kind of great astronomer of the Roman era was Claudius Ptolemy in the year 140. Now he wrote a mammoth compilation of astronomical knowledge, which today is known by the Arabic name Almagest. Now, his most important contribution was a geometric representation of the solar system that predicted the positions of the planets for any desired date and time. Now, Hipparchus, not having enough data on hand to solve the problem himself, had instead amassed observational material for posterity to use. And so, Ptolemy actually supplemented this material with new observations of his own and produced a cosmological model that endured for more than 1,000 years up until the time of Copernicus. And so, what was the thing that he wanted? Well, the thing that he was able to start addressing is this wandering orbits of planets. So remember, the Greeks had called them planets after wanderer. So, the complicating factor in explaining the motion of the planets is that their apparent wandering the sky results from the combination of their own motions with Earth's orbital revolutions. So if we look at this diagram, the letters on the diagram show where Earth and Mars are at different times. And so if you look here, here's Earth's orbit, and here's, for example, Mars. And you can see even though it's kind of A, B, C, D, E, A, B, C, D, E, the observation is not the same. It kind of will start moving up and then kind of almost backtrack before moving onward. And by following the lines through each of Earth's position through the corresponding Mars position, you can really see how the retrograde motion of Mars looks against background stars. So the retrograde motion of planets that are beyond Earth's orbit, if you really want to think about how this actually looks in the night sky, well, they're going to move eastward over the sky over the weeks and months over the sun, but as soon as Earth passes the planet, it actually looks like it's drifting backward. It's moving west in the sky. Now, even though it seems to be moving in the east, the fastest moving Earth really has overtaken it, and it seems to our perspective to be leaving it behind. As Earth rounds its orbit, the planet again takes up its apparent eastward motion in the sky. This temporary apparent westward motion of the planet as Earth swings between it and the sun is what we refer to as retrograde motion. Now, such backward motion is much easier for us to understand today because we have much more tools, much more understanding of the cosmos, but Ptolemy was faced with a far more complex problem of explaining such motion because he assumed that we had a stationary Earth. He was, again, operating under that geocentric model, and so because he had that, he had different constraints that he had to work with. So he came up with a solution. Now, the Greeks believed that the celestial motions had to be in circles. Because remember, the circles and spheres were perfect things. And so he's like, I got to construct my model using circles. So to do that, he actually ended up needing dozens of circles, some moving around other circles in a complex structure that would make you pretty dizzy by comparison. Now, Ptolemy solved the problem by explaining the observed motions of planets by having each planet revolve in a small orbit known as an epicycle. Now, the center of the epicycle that then revolved around the Earth on a smaller circle called a deferent. By choosing the right combination of speeds and distances, Bernoulli actually succeeded in having the planet move westward at the correct speed and for the correct interval of time, thus replicating the retrograde motion with his model. Now, he did have a complicated system, as we already mentioned. When a planet is at a position X on the epicycle orbit, it is moving in the same direction as the center of the epicycle from Earth. The planet would appear to move eastward. When the planet, though, moves to Y, however, the motion is opposite the motion of the epicycle center around Earth. This system is not centered exactly on Earth, but is an offset point called the equant. The Greeks needed this complexity here to explain all the actual motions in the sky because, again, they believed that the Earth was stationary and they believed that the sky motions had to be circular. However, as we're going to see later on, the planets, much like Earth, travel around the Sun in orbits that are actually ellipses and not circles. So, to match the observed motions of planets, Bernoulli had a center of the deferent circles not on Earth, but at some point distant from Earth, again referred to as the equant point. It may be that Bernoulli did not intend for his cosmological model to describe reality, but merely to serve as a mathematical representation that allowed him to predict the positions of the planets at any given time.